Activation energy is a very important part of chemical reactions. Activation energy is the minimum amount of energy required to complete the reaction. So what this means is that even when we have a reaction that happens to be exergonic, so we would call that spontaneous, even in that situation, you are going to have some activation energy that is input into the reaction. So if we go through and look at this diagram here, and I'll point out that activation energy very often is designated EA, or energy of activation. In this example, notice that the reaction that we have, this is going to be an exergonic reaction. And the reason that it's exergonic is because notice the reactants have this amount of energy and the products have a lot less. So you could draw bars on there and turn this into a bar graph if you wanted to. But since the products do have less energy than the reactants, energy would be output or produced or yielded from this particular reaction. So we would call it a spontaneous reaction. However, that does not mean that this is going to be a fast reaction. So if you notice here, when we use a line graph instead of a bar graph to represent this exergonic reaction, we do have this little hill now in here, which we're going to call the activation energy. So this activation energy, again, is this little hill that we have right here. This is energy that is absolutely required if we want this reaction to take place. Now, the reason for this is because when you have a reaction, those reactants down here, they have to reach this transition state. And the transition state, it is an intermediate state, but it is an intermediate, highly unstable state. And so in that intermediate state, that transition state, a lot of times we are flexing bonds or straining chemical bonds, perhaps so they will break a little bit more easily as this reaction proceeds. But since it is highly unstable, it is very high energy. So remember that the higher the instability, the higher the energy. And potential energy is really what we're looking at here. So if our reactants have to reach this transition state, which is the top of the hill, they have to have some energy to actually get up there, because they're not going to end up in a transition state with more potential energy if there is no actual input of energy. So sometimes spontaneous reactions are slow because it does have a very high activation energy. So the higher the activation energy, the slower we expect the reaction to be, at least to get it going. Now, as soon as we get to the top of the hill, so once our reactants get up here to the transition state, the rest of the reaction is very, very fast. So much less than a second would be, because that's like the ball rolling down the hill. That really doesn't require anything much to get it to roll down the hill. But the going up the hill, that was the really tough part. So activation energy, it's always going to be required. Typically, if it's not too much, if it's a rather small hill, this can be supplied as heat. So heat is very often the source of activation energy. And that's why if you do have very warm surroundings, or if you heat up a beaker or test tube, your reactions often will be much, much faster, because you've provided the heat, which is going to enable those reactants to get to their transition state.